the next thing that we can do is find the global and local and global minima and maxima, which is maximum plural or minimum plural. So if we want to find where's the global minimum of this function on the interval, so the first thing we want to do is we want to find everywhere where the derivative is 0, because the places where our derivative is 0 are usually where, if we have a hill like this, then the place where the derivative is 0, is going to be this point where it changes direction, and that is a maximum in this case. So we can use this fact to find candidates for the absolute maximum on an interval. So if we take this function, first thing we want to do is take a derivative and see where does this derivative equal 0. So using the power rule, we get 2x minus 5x plus 2x squared. Sorry, not 2x squared. Nope. Just x squared minus 5x plus 6. Then we set that equal to 0. So now we notice we can factor this as x, not plus x minus 3 and x minus 2 equals 0. So this has zeros at x equals 3 and 2. So we know that those are either maximums or minima. So, or we don't know that for sure, but those are our candidates. So what we can do is we can plug those in to the function and see which one has the higher value or the lower value, because we're determining a global minimum. The global minimum just means it's the bottom of a function. The points around it are higher than it, and that point is lower than any point on the graph, or on this interval, 2 to 5 in this case. So if we plug in 2 to this function, to the function, not the derivative, so we do go here. 2 cubed is 8 times 1/3 is 8 over 3 minus 5 over 2 times 2 squared, which is 4 times 5 over 2, which is 10, minus 10, plus 6 times 2, which is 12, and then plus 4. So if we plug all this in, we get 16 plus 8 over 3, which is 56 over 3, I believe. So this value, we're just going to check it against all of our other candidates. So now we're going to check our other candidate, which is 3. X equals 3. I'll do it up here just to make sure I have room. If we plug in x equals 3, we get 27, or 3 cubed is 27 over 3, so 9. That doesn't look good. I'll just do it down here. 3 cubed, so 9 minus 3 squared is 9 times 5 over 2, it's 45 over 2, plus 6 times 3, which is 18, plus 4. So here we get 31 minus 45 over 2, which is 62 minus 45, 17 over 2. So if we look between these 2 points, this 56 over 3 is bigger than that 17 over 2. Let me just check that to make sure. It's almost 20. Calculators come in handy. 56 over 3. 18. Yeah, it is bigger. But now we know that this is bigger of these 2 candidates, but we also have to consider that this value x equals 5. Oh, sorry, we're looking for the minimum, not the maximum. Oh, oops, we had 56 over 3 and 17 over 2. Sorry, I'm still getting used to Zoom. So we know this one is the smaller value of those two. So that's going to be our best candidate for the minimum so far. But we also have to consider that the graph, the endpoints of this interval could also be the global maximum or minimum on that interval. So we have to plug those in too. Because if we look at this graph, this is the graph of the function. These are our 2 points. And if we were looking for a maximum, let's say, the points where our derivative equals 0 would be here and here. But neither of those is the maximum on this interval. The maximum is really up here, so which is our endpoint. So we need to make sure to plug in our endpoints as well. So to plug in our endpoint, we'll plug in 5. So 5 times 5 to the third is 125. Doesn't divide by 3. Over 3 minus 25 minus 125 over 2 plus 6 times 5, 30 plus 4. So we have, if we find the common denominator, we get 250 over 6 minus 125 times 3. 375 over 6. So then we get negative 125 over 6 plus 34. And you could calculate this, but actually, no, you do need to calculate it. So 34 times 6, we're just going to use 34 times 6. We're just going to use regular multiplication because we don't get to use a calculator. 4, 24, 204. And then we do 204 minus 125. 79 over 6. 79 over 6. So if we look, that is not smaller than 17 over 2. So we know that this 17 over 2 is our global minimum on that interval. So 17 over 2, that's equal to, let's look at the graph. So our absolute minimum is going to be here at 8.5. 8.5. So 1 over 3x cubed. Global minimum. Oh, sorry. We're not looking for the y value. The question is just asking us what x value this occurs at. So if we remember, this occurred at x equals 3. So x equals 3 is going to be our, because if they just gave us the y values, we'd just be able to pick which one is the smallest. So if we pick x equals 3, that is our global minimum. Hopefully you could follow all that math. But it's just plugging in numbers based on the candidates for when the derivative is equal to 0. So next we're going to look at concavity. Concavity basically just examines how a function curves up or downward. So here, if you notice, it looks kind of like a bowl facing upwards. So that's concave up is what we call it. And that means that the second derivative of this function is positive. And conversely, if we have a bowl that's pointing down, like over here, then it's going to be concave down with a negative second derivative. And down here, this is a big bowl facing upwards. So it's going to be concave up for the majority of this part. So now how do we calculate this? I kind of alluded to it. It's where if we're looking for it on an interval, we find out where the second derivative is equal to 0. So we can see where this concavity changes sign. So we can find out when it's positive and when it's negative. So let's find the intervals of concavity for this curve. We can find it because we have the graph here, but let's do it analytically because we might not always be given the graph. So to compute the second derivative, we can use the power rule. First derivative is 2x cubed minus 3x plus 1 squared times the derivative of x plus 1, which is just 1. So I'm not going to include that, minus 6x. And then if we take another derivative, we have 6x squared minus 6x plus 1 minus 6. And this is our function. So we want to see where this changes direction, or we want to see where this changes 0 and changes signs, so we can find the intervals of concavity. So when we multiply this out, we get 6x squared minus 6x plus 6 minus 6. So these two cross out, and we're left with, when we take out a factor of 6x, we have 6x times x minus 1 equals 0. So now we're going to look for when this function changes direction, this second derivative function, because that's going to give us an indication of when something is going to be concave, change from concave down to concave up, or vice versa. So if we plug in some really low value, we know that our zeros are x equals 0 and 1, because that's what would make this 0. So if we plug in something less than 0, let's say -1, then we have -6 times -2, which is a positive number. It's 12. We don't care that it's 12. We just care that it's positive. So we know that, and it doesn't change direction at any point before that. So we know that from -infinity to when x is in between -infinity and 0, f is concave up because the second derivative is positive. CC up just means concave up. It's an abbreviation. I'm not sure if you can say that on the AP exam. I'd be safe and just write the whole thing out. But for our purposes, this will work. So now if we plug in a number that's in between 0 and 1, we get, let's say, 0.5. So 3 times -0.5 equals a negative number. So we know that it's that between 0 and 1, f is concave down because the second derivative is negative. It's kind of like what we did for our speeding up and slowing down in unit 4. And now we have one more interval between 1 and infinity. So if we plug in a value, let's say 2, we get 12 times 1 is a positive number. So then between when x is between 1 and infinity, so when x is greater than 1, f is concave up. If we look at the graph, this is true at our point at our point 0. So the function is concave up. It doesn't look like it's concave up, but the whole time it's slowly getting less steep. The derivative is increasing. And then up here it curves up. And then at this point, 0, we said, it starts to get concave down and curve downwards. And then at -1, or at the point x equals 1, then it starts to curve back up again. So this is what this analysis can tell us. just when a function is curving up and when it's curving down.